The last type of converter we're going to look at is our push-pull converter. And so here's a circuit of a basic push-pull converter to sort of illustrate some of the basic concepts. So right away we can see in the middle of this diagram we have a transformer. So our transformer has a couple advantages. So we're using a transformer. And so one thing that provides is dielectric isolation. So if we can dielectrically isolate or electrically isolate our DC to DC converters from our AC utility line, so let's say if we're using this to isolate subsequent converters from our utility line, so maybe we have this as our first stage and then we're using other types of converters after this, of course that's going to be safer. So we have improved safety, but also we can have switching speeds that are operating at around 50 kHz instead of our 60 or 50 Hertz for our AC signal. So if we have a DC input on the left at 50 kHz, and we'll talk about what that is, how we get that using these two switches. But if we have a high frequency signal and we're using a transformer to send that across to our secondary side, compared to our 50 or 60 Hertz utility lines, that means we need smaller cores and smaller windings for our transformer. And so of course ultimately that translates to being cheaper and taking up less space, less physical space. So just like with our buck boost converter, we're not going to go into much detail here, but let's talk about some general advantages, disadvantages, general functionalities. So this push-pull converter is not going to be suitable for making major adjustments. So as I said, we can often have this followed by maybe a buck converter or a boost converter, some other type of converter after we do this. One of the big advantages is having that dielectric isolation that's provided by our transformer. So not suitable for making major adjustments of V raw, so we can pair it with another type of converter. One advantage of this is we'll notice, so let's come up here and talk about our circuit for a little bit. On our input side, so over here on the right, you'll notice we have two switches, S1 and S2. Each one is in parallel with the diode, and so the diode is just to prevent current from flowing in that direction when the switch is open. And so if we think about this operation, we have only one switch closed at a time. And so what that's going to do is that's going to create approximately a square wave. So we can call that an AC square wave. So we get S1 and S2 are alternately switching. And what we get is approximately an AC square wave. So a couple of things to note about the approximate square wave and our switching here is compared to all the converters we've looked at up to this point, we only have the one switch, which means we're not continuously drawing current from our input. So one advantage of doing the two switches is we're continuously drawing the current, and as sort of an extra bonus to that, of course we're going to get more power transferred, but we're also going to have less harmonics. So we can write that and we can say an advantage of this continuous current draw from our power source. So this is because we're always closing either switch 1 or switch 2, which means we have fewer harmonics compared to our previous converters where we're not continuously drawing, where we have a switch that's disconnecting and then after some time reconnecting. Here, in a perfect world, we'd have S1 and S2, one of the two is always closed. But one other thing that we need to consider is we actually have to plan in some dead time. So we need to include some dead time when both switches are open. So this can be relatively small depending on how well we can control that. So this is when S1 and S2 are open. And so ideally this is a really short time. And so what this does is this is to prevent something called shoot through. And so what happens with our shoot through is essentially our transformer is effectively shorted. So if we come back up here and we look at our two switches, we're going to have equal and opposite flux going through our transformer. So we essentially short that out and we get very large voltage, the entire voltage across both of our switches. And if we talk about using MOSFET devices as switches, of course we can damage those if we have a much larger voltage than we're expecting across them. So we do want to include that dead time, but compared to just having a single switch, we're using a lot more of our input waveform. And so what we see then is we have this approximate AC sine wave, which is coming into sort of our primary side of our transformer. And note I've got sort of dot conventions for our transformer. And we can also note that these are center tap transformers. So I've drawn them so that there's this little space in the middle of the transformer, so that's not to indicate two separate coils, that's just so we can see that we're tapping it in the center. So what we have then is we are transforming over to our secondary side, and let's go ahead and write, of course we know we can relate that voltage on our secondary to the voltage on our primary. And so similar thing for our sort of bottom half, we can say V secondary 2 over V primary 2. And the ratio that relates that is of course our turns ratio between our secondary and primary windings. So of course we have some design there in terms of how we step it up. So now if we look at this circuit, particularly this part right here, we notice that this is something we have seen earlier in our power supply notes where we were talking about rectification. So what this is our full wave center tapped rectifier. So it's taking that approximate square AC square wave and it's going to be rectifying it, and then we see it's passing it on to our inductor and our capacitor, which of course are acting like our storage elements in order to supply a relatively constant current and a relatively constant voltage respectively to whatever load we connect. So this is the basic operation of our push-pull converter. I've not included the plots, but if you'd like to see plots for what some of these currents and voltages look like, you can see page 333 in the Stephen textbook. And so again, we've not gone through this configuration in as much detail as our buck or our boost converter, but certainly if you have further questions about it, feel free to let me know.